Let's take a look at the reactivity series for GCSEs. By the way, there's two different variations of the reactivity series. Well, they're basically the same thing, but there's two different versions that you need to know. Well, no, you don't need to know. It depends on which exam you're taking. If you're taking the normal GCSE exam, the British one for non-international students, you'll be having this one. If you're taking IGCSE, so the international one, so you're not living in the UK but you're doing GCSEs, you'll need to know this one. And this one's specific for the Edexcel one, by the way. Anyways, the two basically are the same, except the IGCSE version, for some reason, has a few more metals that you need to know. Other than that, they're the same. Now this, memorizing it, you need to memorize it. It's really annoying, but you just have to. It's something you have to do, and they don't provide it to you, and there's no way you can find it out yourself. It's not like something you can calculate to find. So here's a tip. If you go to YouTube, there's a video that, there's a song for the reactivity series, basically. If you watch that song, I'll link it down below, you can just memorize it super easily. It's like, first the potassium, sodium. Okay, I'm not gonna embarrass myself here, but anyways, if you watch that video, it'll help you a lot. So just watch that song on the reactivity series. I highly recommend it. Anyways, if you watch that song, by the way, let me just say that some of the order isn't correct, so just make sure you check the orders. And lithium isn't in that song, but you need to add it. This is something you need to know for your IGCSEs and GCSEs too. Just don't forget lithium out there. Anyways, if you'd notice, the reactivity series is for metals, basically. But in the reactivity series, we also have some non-metals like carbon and hydrogen. I'll explain why and what it is right now. So, metals, let's go and do some like background information. Metals have electrons in their outermost shell, right? We call them valence electrons. So metals have valence electrons. You've probably heard of this term before. It's basically just electrons in the outermost shell of the atom. Valence electrons. And they want to get rid of this. They don't like this. So what these guys want to do is they want to get rid of these valence electrons, because remember, this is like basic chemistry now. They want to have a full outer shell of electrons, because that makes them stable and unreactive. That's what atoms, that's the goal, life goal of atoms. So what metals do is when they react with other substances, they get rid of their valence electrons and they form positive ions. So for example, if you had magnesium, I'm only drawing the valence electron, by the way. If you had magnesium with two valence electrons, it can get rid of it and become a 2+ positive ion. And then some non-metal might receive these electrons, because remember, non-metals, they have like 6 to 8 valence electrons. So it's much easier for them to receive 2 electrons than get rid of all these electrons. So non-metals want and metals want to get rid of it. I'll link a video that I did before about this topic. But that's not really the reactivity series. Anyways, so the metals try to get rid of their electrons and they become positive ions. Because remember, electrons are negative. When you get rid of these negative electrons, the overall net charge is going to become positive, right? Because there's fewer negatives. So they become positive ions. Positive ions. And therefore, by the reactivity of the metal, so why was I explaining just basic metals? It's because the reactivity of a metal, by that, sorry, all we mean is how easily the metal forms positive ions. So by reactivity, all we mean is how easily the metal forms positive ions. In other words, how easily it can lose electrons, or how easily the metal reacts with other substances. And this is worth jotting down because it's pretty important. It's basically the main concept of the reactivity series. So metals that form ions easily, right? So the metals that are quite reactive with other substances to lose their electrons, they're going to be near the top of the reactivity series. By the way, the top means it's reactive, and as you go down the reactivity series, you become less reactive. Alright, so gold is going to be very unreactive, and potassium is going to be highly reactive. Now this also explains why gold is so expensive. It's so unreactive, it doesn't rust, it doesn't oxidize, it doesn't do anything. So that's why gold is probably valuable, because it keeps its form really well. Now, we can see the metals in order of the reactivity series. So it goes from most reactive to least reactive in descending. So in descending order. So as you go down, it becomes less reactive. Now let's take a look at some of the trends that are part of the reactivity series. So what trends we can see from looking at it. So if I copy this reactivity series over, we can see that potassium, sodium, and lithium over here, these three guys, they're part of group 1. Watch my video on the periodic table if you don't remember, but remember the group number tells you how many valence electrons there are. So potassium, sodium, and lithium, they're group 1 in the periodic table. So they only need to lose 1 electron. That kind of explains why they're the most reactive, right? It's going to be easy to lose 1 electron. Then we have calcium and magnesium. They're in group 2. They only need to lose 2 electrons. That's why they're second most reactive. Aluminum is in group 3. So it needs to lose 3 electrons. Now does it kind of make sense? The more electrons you need to lose, the more energy, the more stuff you need, right? It's going to be harder, so it's going to make it less reactive. Then we have just carbon and hydrogen for comparison. I'll explain. We'll look at this Y in just a second. Then we have zinc, iron, and also copper, silver, and gold. They are both transition metals. Now, transition metals have like really strange properties. Their electron configuration is weird. You don't really need to know any of that. Just know that transition metals have the lowest reactivity. But you'll notice that not all the group 1 metals are included here. Not all the group 2 metals are included here. Not all group 3, not all transition metals are included here. Because this is basically a simplified version of the reactivity series that containing only the elements you need to know for your GCSEs. That's why I said it's like hard to calculate it. And anyways, if you had group 1, say we had sodium first and then we had potassium, well, it doesn't go in that order. You see, it's kind of strange, right? So that's why I was saying that you can't calculate it. I've also tried to find out if there's a way to calculate it, but there isn't. So just try and watch that video on the song. That really helps in my opinion. But just understand that the overall trend, the fewer valence electrons you have, the more reactive you are. All right? Okay. And carbon and hydrogen, as aforementioned, these are non-metals. So, to figure out the arrangement, so for your GCSEs, you need to know how to figure out the reactivity series. By that, I don't mean just getting a list of elements and how to calculate the reactivity. There's actually an experiment that you need to do. That's why I was saying you can't calculate it, because you need to do an experiment. In your GCSE exam hall, you're not going to be there with a bunch of elements and you're not going to be calculating them and doing experiments to find it out, are you? So to figure out the arrangement of metals in the reactivity series, you can react each of the metals with either acids or water. React the metal with either. There's basically 2 methods, but there's a difference. You'll use it for different purposes. You can react them with acids, or you can react them with water. Alright, react the metal with either acids or water. By acids, we mean hydrochloric acid. You could also want sulfuric acid, but hydrochloric acid is the easiest to remember and it's the most common. So react the metal with either hydrochloric acid or water. Water is just H2O, right? I'll write that down just in case. So what do we do? So you can react the metal with each of either the acid or the water, and you can see how fast or violent the reactions are. So when you put acid with the metal, see how fast or violent the reactions are. So one might produce a lot of bubbles, one might catch on fire. And so basically the most fair way, the most accurate way of measuring this will basically be temperature. Because it's quantitative, right? It's something you can actually measure. It's not something you just see and just look and see, you just describe. You can physically measure the temperature of the metal. So once you add an acid to the metal, you can see the temperature change. Obviously, the higher temperature change, the more reactive. Lower the temperature change, less reactive, right? So let's take an example. Now let's make a general example first. We will take the metal. This is for the one with acids, by the way. So for acids, metal plus the acid, that's going to go to form a salt. This is something you just have to know. When a metal reacts with an acid, it always forms a salt and it produces hydrogen gas. Alright? So when the metal reacts with an acid, such as hydrochloric acid, it's going to form a salt and hydrogen gas. Let's take a look at an example. Let's say we had potassium react with hydrochloric acid to go and form. What would it form? Well, we said it's going to form a salt and hydrogen gas, right? Well, the hydrogen gas is going to be the same. Well, what would the salt be? It's going to be potassium chloride. Potassium chloride. Goes to form potassium chloride. Because this hydrogen gas in hydrochloric acid, right? That's just going to go to form the hydrogen. So we have potassium and we have the chlorine left. So the two are going to react and they're going to form potassium chloride. In equation form, we're going to have two potassiums react with two hydrochloric acids. So if I remove the two, the reason I have the numbers in front is because we need to balance the equations, right? The reactants and the products, they have to be the same amount. I'll balance it after. Potassium plus hydrochloric acid will form it'll form potassium chloride, the salt. So this is the salt, and hydrogen gas. Hydrogen always exists in pairs. That's why it's H2. Well, if we balance it, we have two hydrogens here and one hydrogen here. So we need to add a 2 here, don't we? Let me balance it using red so they can clearly see the balancing equation part. I'm pretty sure I made a video on balancing equations, so if you don't know, just watch my video on that. Two hydrogens. Well, now we have two chlorines here and one chlorine here. So this is going to have to become 2 as well. But then we have two potassiums and one potassium, so this becomes a 2 as well. That's why it's 2K, 2HCl, 2KCl, and H2. That's pretty much it. So this will be the salt, hydrogen gas, hydrochloric acid, and the potassium. Right? And then you can see the reactivity process. So potassium, if you remember the reactivity series, potassium is at the top of the reactivity series. It's the most reactive. Therefore, when it reacts, it's going to react explosively. Potassium, let me just copy down the reactivity series again. Potassium is at the top of the reactivity series, right? Let me just move this over. And, sorry, bear with me. Potassium is at the top of the reactivity. So it means it's going to be the most reactive out of all these metals, right? So it reacts explosively. Potassium reacts explosively. It can potentially catch on fire. And it whizzes around. Whizzes around producing hydrogen. Because remember, it reacts the metal plus the hydrochloric acid goes to form salt plus hydrogen gas. Right? So it's going to react explosively. It's going to produce a salt, but it also produces hydrogen gas. You just need to understand that the higher in the reactivity series, it's going to be more explosive. As you go down, it's going to be less explosive. So by the time you get to maybe magnesium, this is going to produce loads of bubbles. As you go even down, further down, zinc and iron, fewer bubbles. And by the time you get all the way down to copper, it usually won't even react with hydrochloric acid, because that's just how unreactive they are. So up to maybe iron, you might have bubbles being produced, and as you go down, obviously fewer bubbles will be produced, and then by the time you get to copper, it won't even react. So gold obviously is the least reactive, so that's why it's expensive as well. As you go up, more explosive, more fire, etc. Right? But when you do this experiment, you just need to ensure one thing. It's a fair test. Fair test. You probably did fair testing when you were in Key Stage 3 or Key Stage 2 even in primary school. probably learned that you have to keep the control variables, everything the same, right? So except your metal that you're changing, everything else needs to be the same. So same amount of hydrochloric acid and the same concentration too. Even if it's the same amount, if one experiment is done using much more concentrated hydrochloric acid, it's going to give varying results, right? Same hydrochloric acid, so keep that type of acid the same with the same amount and concentration of it. Same surface area. So this, although we are changing the metal, right? You need to keep the same mass of the metal, use the same amount of it, but also the surface area. If one has a greater surface area, it's going to have more space to react with the hydrochloric acid, right? Same surface area, same mass. And yeah, that's pretty much it. And also, of course, the same type of acids and stuff. Alternatively, we said we can react it with water as well, right? You can react the metals with either acids or with water. When you react metals with water, alright, my spelling is terrible, with water, you know what, let me write that in full. I'm worried someone's going to get confused. Reacting metals with water, so rather than acids, we're going to have metals plus water, right? Because it's reacting with water rather than the hydrochloric acid from before. What would it produce? It produces a metal hydroxide. But the constant between both the acid and the water is they both produce hydrogen gas. Alright? So, lithium. Let's do an example with lithium. Lithium can react with the water, H2O, to form a metal hydroxide. Well, we're going to have the hydrogen gas being produced over here, right? What would it have? We're going to have lithium and oxygen. But we also have a hydroxide being produced. Hydroxide suggests that we're going to have hydrogen in there, right? Hydrogen. This is produced, LiOH. It's called a lithium hydroxide. So when you have lithium reacting with water, it's going to have lithium hydroxide. It's not just lithium and hydrogen. It's lithium, hydrogen, and oxygen. And it's also hydrogen gas being produced. But you'll notice the equation isn't balanced, so we have to balance it out. We have one lithium here, one lithium here. One oxygen here, one oxygen here. Two hydrogens here, two hydrogens here. But notice, we have three hydrogens. One and two hydrogens here. So this needs to become greater, right? Well, we can't make 2 become a 3, so we're going to have to use the nearest one, which is a 2. That'll make 4 hydrogens. 2 hydrogens already here, so we're going to multiply this by 2 to create 4 hydrogens. At least the hydrogens are balanced now. But now we have 2 lithiums and 1 lithium here. So let's balance the lithium out. 2 oxygens as well. 2 oxygens. And then, yeah, now everything's balanced. So, the thing is, obviously water is less acidic than acids, right? Such as hydrochloric acid. So the important thing you need to know is that only the reactive metals, only most reactive metals can react with water. Because you need to be quite reactive to react with water, right? Water is just water. That is going to be potassium, sodium, lithium, calcium, and magnesium to an extent. Magnesium, it basically doesn't react, it's just very slightly. So you can almost say it doesn't react, but I'll include it there anyways. It very slightly reacts. Slightly, yeah. So if we bring back the reactivity series that we had before, you can kind of sketch out a bit of a diagram for the reactions that would occur. So for the reaction with acids, we said maybe up to iron. Let's start with water first, because the water is going to have the least reactivity. So maybe up to magnesium. Up to here, reacts with H2O, water. Magnesium very slightly, remember. And then we have acids. Acids react decently up to iron. So it more or less reacts. That's going to be the hydrochloric acid, right? So up to iron, it more or less reacts. Up to magnesium, more or less. I'll put it halfway here. because magnesium not fully. And then we also have oxidization reactions. That's when it reacts with air. Well, basically everything reacts with air except gold. Remember, gold doesn't really rust. Silver kind of reacts. So I'll put it there as well, halfway there. O2, oxygen. So when metals react with oxygen, metal plus oxygen, you form a metal oxide. That's what happens to iron. When iron reacts with oxygen, we form Fe2O3, I believe. Let me just double check that. Yeah, Fe2O3. It forms this thing, this metal oxide. This is more commonly known as rust. You know that orangey thing that you see on old metal? That's rust. That's when the metal, the iron, is reacting with oxygen to form Fe2O3. But the rust isn't for all the metals, it's more specific for iron. Alright? So you kind of need to know this rough trend. It'll be up to magnesium where it reacts with water. So the overall trend is the more reactive you are, the more things you can react with. Potassium is going to react with basically everything. And then the lower you go, the lower you go in the reactivity series, the less reactive they become, so they react with fewer things. That's basically the key point. And gold reacts with basically nothing, not even oxygen, hence being more expensive, because it keeps its form really well. Anyways, thanks for watching this video on the reactivity series.